Today we are going to solve the self-inductance problem of two parallel wires. These two long parallel wires, each of radius a, whose centers are at a distance d apart, both carry equal currents in opposite directions. They are asking us to find the self-inductance of the length L of such a pair of wires. In order to do that, we need to remember the equation for self-inductance, that's the magnetic flux over the current. So if you do the right-hand rule, we can know that this flowing current, this wire, will create a magnetic field by the right-hand rule going out of the screen, right? If you do the same in this wire, the current going in that way, by the right-hand rule, we'll know that the magnetic flux created by this wire, this current, will be going also out of the screen. That will be the magnetic flux. So then, that will be the magnetic field in that point. Now, by Ampere's law, we know that the magnetic field created by a wire is equal to B mu naught times the current, or 2P times the distance. But we are going to define from here to that point, I'm going to say that that will be R. Then the distance from the center of this wire to that point will be R. Since we also have a magnetic field created by the other wire, we have to add this magnetic field. So then we have mu naught times the current 2P, and this distance will be D minus R. So D minus R. Okay, so once we have that, we'll need to calculate the magnetic flux throughout this area that I'm gonna represent here. So the magnetic flux will be the integral surface of B dot dA. Since the B field is going out of the screen and dA is also going out of the screen, the cosine of that angle will be 1. So that's positive. Now I have to replace dA. dA is equal to L, that's this distance, times dr. That will be changing. So I'm gonna say that this is a specific area that is changing in time. Then I have to replace the magnetic field that we already found by Ampere's law. Then when I have the self-integral surface of current, in order to simplify that equation, I'm gonna make a common factor of the constants. Then I have that mu naught times the current, that's equal in both wires, over 2P. And I was forgetting the L, so the length of the wire, so that there it is. Now I have to do the math, and before that I have to know the limits of this integral. So I'm going to find the magnetic flux in this area, starting from A, right? Starting from A, that's A, and I will end at this point. So that will be D minus A. Okay, D minus A. A, D minus A. Now we have to calculate that integral, and we know that the integral of 1 over R will be natural log of R. slightly changing t minus a. Now we have to calculate the interval of 1 over d minus r, and to do that we have to use substitution. So du d minus r, and then I have minus dr and minus du dr. In replacing that, I have as it follows: natural log of d minus r, d minus a, and a. Replacing the limits, we have it will be natural log of d minus a over a. And here we have d minus a plus a, natural log a over d minus a. Now to simplify that, constant now I'm going to raise that natural log to minus 1, and I have this positive natural log of d minus a over a, and these two natural logs are equal, so then I have these two natural logs are equal, so then I have 2 mu naught current L to P natural log d minus a over a. Simplify that, and I have that the magnetic flux will be mu naught times the current times the length over P natural log of d minus a over a. And the self-inductance will be the magnetic flux not over P natural log d minus a over the current. So simplify that. So then I will say that the self-inductance of these two wires over the length L will be driven by this expression. That's all. Thank you for watching. Thumbs up and subscribe. Thank you.